Welcome to Mastering Solutions. I've drawn the picture of what's happening in our question, and they want us to use ray tracing to figure out the location of the image and if it's real or virtual or upright and inverted. If you were really precise and drew this to scale, you could figure out exactly where it's going to be with a numerical value. We're not going to be that precise here, so I'll also show you at the end how to calculate the distance using the thin lens formula. But the three things that you need to remember when you're doing any ray tracing is you need to remember parallel to focal point, and then center of the lens, and then focal point to parallel. If you remember that, say it over and over and over, that will get you through any ray tracing. Now, sometimes it can get confusing when you're doing the ray tracing, but if you just remember this and walk yourself through it, you'll be able to get there. This one is a little bit more involved than the last one, and so it's important to practice these ones. Starting off, we're going to draw a parallel line from the top of our image. Since it's a parallel light ray, it's going to focus precisely at the focal point of the lens, right there. Now, that's not where our image is going to be since we're on the inside of the focal point. So we have to extrapolate this back. I'll draw a solid line just so we can see it a little bit more precisely. So we can extrapolate it back over here. And then now we're going to draw through the center of the lens. And so you can see the lines are diverging from each other because we're on the inside of the focal point for the converging lens. So we're going to do the same thing. We're going to extrapolate this line back as well. We'll do our best that we can. Looks pretty decent. And so now the last one, we go from the focal point and then it's going to go parallel. But since we're on the inside, we're going to do the extrapolating first, and then it'll come along here at the same line. And now, since it's coming from the focal point, it's going to go parallel. And again, we'll extrapolate this line back. And since I didn't draw exactly to scale, you can see that I'm a little bit off, but if I had done it a little bit more precisely, all three of them would have come to focus right here. And so we would have been able to see the object location and the height, but you get the idea that we're going to get a virtual image because it's on this side of the lens. It's upstream of the lens. And anytime you have a virtual image, it's going to be upright. And so that is the answer. Now let's figure out the precise location of the image here using the thin lens formula. So we're trying to solve for the image. And so we know 1 over f is equal to 1 over s plus 1 over s prime. This is what we're trying to isolate. So if we minus over 1 over s, we get 1 over s prime is equal to 1 over the focal point minus 1 over the object distance. And so when we plug in our numbers, 1 over the image distance is equal to 1 over the focal point, which we said was 10 centimeters or 0.1 meters, minus the object distance, which is 6 centimeters. So we could say 6 times 10 to the negative 2 meters. And so when we calculate that, we get 1 divided by 0.1. Now the object distance was upstream of the lens, so it's going to be a positive value here by convention. And so we're going to minus then 1 divided by 0.06, or you could do 6 times 10 to the negative 2. And so that gives us a negative 6.67 diopters for the location. But we need to take the inverse of that because this is representative of 1 over s prime, not s prime itself. So 1 divided by the answer gives us a negative 0.15 meters or negative 15 centimeters. The 15 is agreeing with the fact that we have a virtual upright image, and it means that it's on this side of the lens for the image. Typically, the images, if they're positive, will be downstream of the lens. If they're upstream of the lens, they will be negative. And so this is the location of the image. And then we have a virtual image that is upright as well for this converging lens.